All right, this is Dr. Martin, and this is the video I did for DSD for Friday, although it's Sunday. So I had to go up to Austin on Saturday, and I just didn't get this done. And we had 20 medical and dental students over Friday night, so I didn't get it done then either. So I'm doing it now. And what I did actually is I went back and dug up a video I did in 2020 for the fall 20 DSD class when I did the review, which is basically what I did in class the other day. And so I went over one of the old tests. And so I think that's going to be as effective as this one. And so I just wanted to introduce it, and then I'm going to play that video. So here we go. You should know operators in C. So maybe I'll switch this over here. We'll look at a few of these. Okay, so operators in C. So here's an example. A logically ANDed with B, logically ANDed with C, evaluates to B tick or 4 tick B 0001. All right. Now I did have a question. Somebody asked me, what are those 4 tick H and 4 tick B? So we went over this. We did a whole lecture on all the exigencies involved in creating constants. This is how you do constants in Verilog. Okay, you put a number. That's the number of bits. It's not the number of digits. So if you do hex, you do 4 tick H. That doesn't mean you get 4 hex digits. It's still 4 bits. The first number is always the number of bits, and if you don't put it, it's assumed to be 32. Then you put a tick, and then you put the radix. In this case, B for binary, H for hex, D for decimal, O for octal. And then you type in your number. And you should try and make the number of digits you type in correspond to the number of bits. So if you do like 8 tick H, you should have 2 hex digits. Because if you have more or less than, and then there's also issues with if you make it signed, it can get really crazy. So try and make sure you match up the number of bits with the number of bits you actually define, whether it's in hex or decimal or whether it's in binary. Okay, so here are the original definitions. A is 0011, B is A, so that's 1010, and C is 0010. All right, so if we logically AND A and B and C together, what do we get? And this is true. We get 1, because a logical operator takes the arguments and only looks at whether they're zeros or something other than 0. If they're 0, it's considered false. If they're true, if they're non-zero, they're considered true. And so this always returns only one of 2 possible outcomes. A logical operator always returns one of 2 outcomes, 0 or 1. Nothing else. There's no in between. You either get a 0 or you get a 1. You don't get all ones. You don't get F. You just get 0 or you get 1. That's it. Okay, so obviously A is not 0, B is not 0, and C is not 0. So the logical AND of these 3 always is going to evaluate to true or 1. Next, B bitwise ANDed with C evaluates to 0010. Okay, let's look. So B is 1010 and C is 0010. So the first one, the 10, doesn't overlap with the 1 in here when you do it bitwise. So that's 1 ANDed with 0, that's 0. 0 ANDed with 0, that's 0. 1 ANDed with 1, that's 1. And 0 ANDed with 0, that's 0. So it's obviously going to evaluate to 0010. Okay, next, a tilde B is a bitwise inversion of B. So here's B. B is A. Anytime you inverse an A, you get 5. And so it's going to evaluate to 4 tick X5. All right, so that's a good question. So what does the X mean? Okay, so this one's a little bit tricky, but what you should see there is that that if you do a bitwise inversion of B, it should evaluate to 4 tick H5. not X5. The X means unknown. So that's really goofy. So what that's basically saying is an unknown bit plus, so there's no radix specified. So the when the radix is not specified, it defaults to decimal. So basically, you're saying decimal X5. Well, so basically that's the first bit's unknown, and then you have 101. So that's what it defaults to, and that's not correct because it actually the tilde B, since B is 1010, turns out to be 0101. So the first bit is not X. So anyway, so that's false. Okay, not B is obviously 0. And 4 tick X0, that's not correct either because the X is not a hex designator. So that's false. That would be unknown, but it's known. It's a 0. It's 0000. E. A ORed with C evaluates to A. All right, so A and C, yes, it's going to be, A and C, no. So A and C does not evaluate to A. When you OR A and C, A is 3, C is 2, and you wind up with 3. So it evaluates to 3. Oh, well, that is A. My bad. So yes, it does evaluate to A, so it's true. A logically OR with C evaluates to 1. Yes, that's right. 1 shifted 0 evaluates to B, 4 tick B 0001. Yes, that's correct. Explanation point A evaluates to 0. Yes, that's correct because it's a logical inverse. A is true, so the logical inverse is false, and that's always 0. If B bitwise ANDed with C begin end will evaluate to true and execute. So let's look. B ANDed with C. So B is 1010 and C is 0010. So they overlap at a 1 in bit position 1 if you count the first position 0, 0, 1, 2, 3. So they both have a 1 in position 1. Therefore, they will evaluate to true logically, and so they don't. You're bitwise ANDing them. So you get 0010, which is not 0, so that would be true. And so therefore the if statement is true, it does execute. So that's true. A bitwise ANDed with B evaluates to 1001. Well, A is 0011 and B is 1010. So what they're going to evaluate to is not 1001. That's incorrect. Their bitwise ANDing is going to give you 0010 for A and B. And then let's see. Then the last one here, A bitwise ANDed with the bitwise inversion of C. So we take C, which is 0010, you invert it bitwise, so that's 1101. Then you're going to AND it with A, which is 3, so 1101. So that's only going to overlap in the lowest order bit. So that's going to evaluate to 4 tick B 0001. That is correct. Oh, wait, yeah, that's right. Yep. All right. Mark with an X whether the statement is an advantage for an FPGA or an ASIC using an F or an A. So F means it's an advantage for FPGA, and A means it's an advantage for an application-specific integrated circuit, which would be just a regular integrated circuit or even a mass programmable integrated circuit. All right, cheaper and small production runs. Clearly an FPGA. If you're going to do lots and lots, you can afford to have the foundry do these for you. But if you're not going to do lots, you really can't afford to go through the cost of firing the foundry up to make your chips. All right, so best choice for product where the clock rates are pushing the limits. If you really have to push the limits in clock rates, then you probably do want to avoid an FPGA because the routing can be quite complicated and can screw up your timing since you're typically running your signals around a big connection interconnect matrix. Whereas in a dedicated chip, you're going to control the actual routing of every line, and or at least you can, and you need to then you can push the timing to the limits. Have much smaller chip area for the same circuit. So obviously, chip area is large for an FPGA because you have to include all the programmability hardware. So that would be an advantage to the ASIC. Usually take longer to get a product to market. Yeah, if you're going to have the foundry involved, it's going to take longer. If you can just buy off-the-shelf parts, program them on your bench, you can certainly do that a lot faster. Best choice when multiple prototypes are planned. Yeah, when you're prototyping, you sure don't want to be running through an entire tool up for a foundry to do a production run for a single chip or two. That would be just prohibitive. Will likely be cheaper in very large production runs. Okay, that would be an ASIC. Clearly, in large production runs, the FPGA is going to get pricey because they're going to be more costly per chip than what you can make to do the same thing. All right, best choice where ability for field updates and changes are required. Okay, no choice. You have to have an FPGA. Best choice where clock skew would not be a big problem. FPGA, if you don't care about a little bit of clock skew, which means your clock goes through a longer path and might be delayed just slightly, then you're perfectly happy with the synthesizer routing your clock in some circuitous way through the interconnect matrix. So that's clearly true. Best choice where all the work must be in-house for security reasons. Yeah, if you're going to do that, then an FPGA would be nice. Best choice where the target is a large consumer market looking for the cheapest price point. Okay, so now if you're going to sell lots and lots of them, you're going to go with a dedicated chip. All right, how big would a ROM have to be to hold 300 2's complement integers that could vary from -100 to +100? Well, okay, so it's a good question. So how do we do this? Well, first we take the log base 2 of 300. We'll find that the nearest power of 2 is going to be 512 because 256 is too small. So we have to double that. That's 512. So 512 is going to have 9 address lines, and then so we need at least 300 locations to store them. But how many bits do we need to hold plus or minus 200? Well, that's minus 100 plus 200. Minus 100 to plus 100. So that's 200 things, or 201 things actually, counting 0. And so as a result, we need 256. So that's 8 bits. So you need a byte, and we need 512. So how many address lines? 9. How many output data lines? 8. How many rows? 512. How many columns? 8. Same as the output data lines. Okay, what questions should you ask when you decide for either a read-only memory, a standard factory programmable, an erasable programmable read-only memory that would be, say, ultraviolet erasable, electrically erasable, electrically programmable read-only memory, or a flash, which is also an EEPROM? Does it need to be reprogrammed? So yeah, you would want that. You'd want that. Yeah. Well, you definitely want to know that before you decide what technology you're going for. So yes, that's true. You need to ask that question. Do we need to change individual locations? Yeah, if you're going to do flash, you can't change individual locations. If you're going to do a factory programmed ROM, you can't change individual locations. But with an EEPROM, you can't do that. You can't erase individual locations. You have to erase the whole chip. But with an EEPROM, you can. So yeah, you definitely want to ask that question. Do we need the cheapest technology for a very large production run? Yes, that's another good question. you would probably want to ask that and make sure that that you ordered a read-only memory if you were going to do that, because you don't need to reprogram it and you want to get the cheapest you can, and it's going to be a very large run. So then that would justify factory programming. Is size a critical issue? That's probably less of a question. How many I/O pins will we need? Yeah, that's also something you might want to ask, whether you're going to get it connected by, say, I2C, or whether you're going to have a parallel interface to it. And does it have to work underwater? It doesn't have anything to do with these. You just have to, that has to do with sealing it up nice and tidy. Okay, answer a few questions about the Nexus 4 board. How fast is the onboard clock? Well, I'll leave that to you to figure out. You should already know. Mark with an X, the FPGA has about how many pins? It has 325 pins, but a bunch of them are power pins. But it does have 325 pins. And by the time you subtract off the power pins, you still have quite a few GPIO pins that you can utilize. Our constraint file typically has set the I/O pins up for which standard? Usually low voltage CMOS 3.3. That's what we typically have been using. How many slide switches and LEDs are available for use total? Okay, so there's 16 slide switches and 16 LEDs. Plus then there are some RGB LEDs as well. So that was a little bit of a goofy question, but I was basically thinking about 16 plus 16 equals 32. But you do have, I think there are actually two RGBs, LEDs, as I recall. Yeah, there are two. So you could add another 6 if you wanted. All right, so a bad question, really. How many control lines go to the row of 8 7-segment displays? So that's a good question. So how many control lines do you need for all 8 7-segment displays? Well, you need 8 control lines for the segments and 8 control lines for the common anodes. So you need 16. The question's not stated in a great way, though. What are some of the major steps in the design flow to get your code actually working? Well, so if you look at the at Vivado, you should be able just to go through that. But obviously, we can elaborate the design. We can simulate the code. We can synthesize the code. We can do a post-synthesis simulation. Then we can implement the design. We can do the placing, the mapping, placing, and routing, and then we can generate the bit stream, and then we can program the board. We use files with each lab project in Vivado. What file connects the top-level ports to actual pins? That's this constraint file, right? And in fact, where do you find out whether the pin's an input or an output? You find that in the top module's port list. What file is the main module? What file has the main module and submodules? Well, that's your source file. Unless you have multiple source files, and then you'd have to talk about that. What is the file that is written to the Nexus 4 board? Well, the file that's written to the board is the .bit, the .bit file. Which file is used to run the simulation? You use the test bench, and then you instantiate your top-level module. There are two ways to list variables when you instantiate a submodule. Yes, there's the positional notation, and there's the name notation or dot notation. Here's an example instantiation. Which type of instantiation is used here? Well, since there's no dots, it's not the dot notation. It's not the name notation because there's no names in parentheses. So that's obviously positional. Okay, answer the following about always blocks. The left-hand signals in an assign statement have to be wires. No, that's... oh, yeah. Well... Yeah. Okay, bad question. If it's inside an always block, they have to be registers. But if it's outside an always block, they have to be wires. Okay, the at star is typically used in blocks that result in sequential logic. No, they typically use them in blocks that result in combinational logic. The always at pos edge clock, comma set not. This statement has a problem. Yeah, your set not must also be an edge signal, and so you have to specify that. I know some at least one student said they had problems using the push button, even calling it an edge. I'm a little confused about that, but it should have been legal, so I don't know what was going on there. The right-hand signals in an always block have to be wires. No, they can be wires or registers. The always at pos edge clock neg edge set not. This statement has a problem. No, that statement's fine. It should be good. When we have a set not out of the sensitivity list, when we leave a set not out of the sensitivity list, this means it is a synchronous set. Yes, that's correct. Active low synchronous set. It is a general rule to use non-blocking assignments in always blocks intended to be sequential. Yes, generally we do use non-blocking, but you'll notice in the practicum, I actually had some blocking statements in one of my always blocks because I was summing things up and I needed one statement to complete before the next statement used the answer to the first statement and added the third variable to that. Okay. We can use the test question mark if true test colon result if false construct only in an always block. No. We can definitely use that outside always blocks. That's the question mark colon syntax, and you can nest those too. We can use case statements in or out of an always block. Nope, that's not true. They must be inside an always block. We can use if statements only in always blocks. Yes, that is correct. We can only use if statements in always blocks, but you can use them in an always block, and then they don't necessarily have to result. In sequential logic. They could result in combinational logic. Okay. Continuous assignment statements. They can be used for modeling combinational logic. Yes, that's usually what we do. They are outside procedural blocks, always in initial blocks. Yes, we generally put continuous assignment statements are outside the always blocks. The continuous assignment executes when any right side signal changes. Yes, that's correct. The left-hand side of a continuous assignment must be wire data type. Yes, it must be wire data type. It cannot be a register. Assign #5 carry sum equals a plus b. This is a continuous assignment. Yes, it is. The above statement has a 5 nanosecond inertial delay. Yes, it does. The above statement has a 5 nanosecond transport delay. No, it does not. Assign pad. Assign pad equals enable question mark data colon 1 tick BZ. If enable is low, this will disconnect pad. So if enable is low, so the assigned pad gets disconnected if enable is low. That is correct. So if enable is low, it's 0. So that's going to give that's going to have it evaluate to false. False is the second operand. 1 tick BZ. So that means you're sending it to a high Z state or disconnected. The above statement could be used for a 3-state buffer. Yeah, it could. The Z value does not synthesize. It's only for simulation. So what do you think? Yeah, that's true. Okay. Well, yeah. Okay. All right, so that's that. Okay. So that's kind of what I wanted to go over there. Let's see. I think what I'll do, that should give you a pretty good feel for what's going to be on it. Let's see. I had some more questions, but I think a lot of these are on here. What's the purpose of putting transport delays and inertial delays in your Verilog code? Well, we do that so that we absolutely can get a reasonable simulation. It's all for simulation. List the advantages and disadvantages using an ASIC rather than FPGA for a project that requires a complex digital design. Well, so primary advantage is ASICs are going to give you faster. You can go through a whole number of prototypes. They're going to be expensive, but in smaller quantities, they're going to be quite a bit cheaper because you have that big one-time fee to fire up the foundry to do your chip. If you're trying to get it out the door quickly, you definitely want to go with a FPGA. If you're trying to market a whole bunch of them and get it down to the cheapest price point you can, you're going to want to go with an application-specific integrated circuit. If you're trying to shrink it down to the smallest size, then you're going to want to probably go with an application-specific integrated circuit. If, on the other hand, you can, if you're not making that many of them, then you definitely would probably want to go the FPGA route. If your timing is super critical and pushing the limits, then you definitely want to go with an ASIC. And if that's not the case, then you could, and depending on how many you're going to make, you maybe could go with an FPGA. How big would a ROM have to be to hold 100 2's complement integers that could vary from -200 to -400? Okay, so you have to hold 1,000. So 1024 ought to work, and you need 401 different things. So that's 512. So basically, your ROM has to have 1,024 words, and the words have to be a total of 9 bits. And you would your address lines would be you'd have to have 10 address lines, and you'd have to have 9 output data lines. Okay. Answer a few questions about the Nexus 4 board. Okay, I think we already covered this. Yeah. All right. I think that's it. I think I'm gonna stop here. That's a pretty good sort of taste of what you're going to see on the quiz, or on the test rather. And so just you can go over this video a couple times. That'll give you, these are the kinds of things you ought to be. So that pretty much concludes the review, and it's a pretty good review for the test. So I think I'm gonna we'll just stop with this, and I'll go ahead and post it. It's about 28 minutes or something like that. We will still do some more review this week, so not to worry. All right, with that, we'll quit.